Deborah, and I'm a physicist. And today I'm going to tell you one weird trick physicists do want you to know. It's called dimensional analysis. And another thing we could say is that it's how to make the units work for you. Now, quite often when I'm talking to intro physics students, they get really annoyed because they've lost points because they don't have units. And they say to me, well, what does it matter if I have units? Obviously, these are the units. Or who cares about the units? And actually, I care about the units. I care about the units a lot. For example, imagine I told you I had 1 sugar. Now, you might assume that meant a sugar packet, but I haven't actually specified. So I could mean a sugar packet, a sugar cube, a cup of sugar, a pound of sugar, several pounds of sugar, a semi-truck full of sugar. And whether or not you want that sugar, 1 sugar, depends entirely on how much it is. If you're baking a cake, a single sugar packet, not very useful. If you're sweetening your coffee, an entire pound of sugar, also not useful. So because when we do physics, we care about problems that are happening in the real world, or could be happening in the real world with real physical quantities, we have to care what their units are. Now, with that disclaimer out of the way, what we're actually going to talk about today is how using dimensional analysis, or understanding the units of a problem, can help you remember formulas you've forgotten and solve problems when you're not sure where to start. Before we go any farther, we have to consider that there are 2 types of units, sort of big categories. And those big categories are base units and derived units. Base units are units you can't break down into any smaller pieces, they just are. You could convert them to another unit system, but you can't break them down any further. They're not made of any parts. So for example, we usually use the International System of Units, or SI in science, where the unit of distance is the meter. I might want to know the unit of distance in feet, and I can do that, that's an easy conversion. But that doesn't actually change that it is a unit of distance. I didn't put any other units in to get that value, I just used a conversion factor. Derived units, on the other hand, are things where the unit is defined based on other units. Derived units are more complex units. There's way too many quantities around us to define each and every unit based on something that is physically out there or that has some kind of constant value. So we define a lot of units in relation to other units. Let's see how this works. These are all of the SI base units. The meter, which is a measure of distance, the kilogram, which is a measure of mass, the second, which is a measure of time. I will note that this is the MKS system, which is most common in science. A lot of astronomers also use the CGS system, where we have the centimeter, the gram, and the second instead. There are some reasons for that, but they're well beyond the scope of this video. We also have the ampere, which is a unit of electrical current, the Kelvin, which is a unit of temperature. 1 Kelvin is the same amount as 1 degree Celsius, but the 0 points are different. The mole, which we don't use much in physics, but you'll know from chemistry, and that's the amount of some kind of substance. And the candela, which we rarely use in its own right, but is a useful unit in other contexts, and that's for luminous intensity. Now, it is immediately obvious that these units do not make up all of the units I want to know about in physics. There's a lot of things I want to know that I can't get from just these base units. So what I do is I combine them to create other units that might be more familiar. Let's take a look at some examples. A Newton is the unit of force. Now, many of you will know from Newton's second law that force is the mass times the acceleration. So it won't surprise you to find out that the Newton is the kilogram times the meter per second squared. A Pascal is a unit of pressure, which many of you may know is force divided by area. So again, not surprising, that's a Newton per meter squared. Or in base units, it's a kilogram per second squared per meter squared. A joule is the unit of energy, and that's a force times a distance. So you have Newton times meter, or kilograms times meter squared per second squared. The watt is a joule per second, that's a unit of power. And that in base units is kilograms times meter squared per second cubed. The coulomb is a unit of electric charge, which is the ampere times the second. The volt is a unit of electric potential, or voltage, which is the joule divided by the coulomb. Energy per charge, which is in base units, kilograms times meter squared per ampere times second cubed. And then another example, the hertz, is the frequency. Now, we could keep doing this all night, but I don't think it's especially interesting. There's another way we can modify units that are SI, and that is using the SI prefixes, which let us write down when something is very small or very large. So here are all the SI prefixes for small things. The prefix on the left, and then what that means in scientific notation, and then what that means as just decimal numbers. The font size is smaller for the really tiny ones. Realistically, a lot of these you'll never need to use. The ones you're likely to encounter in physics are centa, as in centimeter, milli, as in millimeter, micro, as in microsecond, nano, as in nanosecond, and maybe pico and femto, depending on what specific applications you're using. Those really, really tiny ones, you're not likely to run into in your sort of physics classroom environment. There's also the big guns. Technically, there are deca and hepto, although you never really see those used. And then kilo, mega, giga, tera, peta, exa, zeta, and yada. In physics, you're likely to deal with kilo, mega, giga, maybe tera. The others, honestly, I mostly see them in high-performance computing. Petabyte, petaflop, exabyte. In physics, we're much more, megawatt, kilogram, kilosecond, etc. Now, I promised at the beginning of this video that dimensional analysis was a weird trick that would help you solve physics problems. And now I'm going to show you how. What we're going to do is we're going to go through 3 examples. The first is going to be a very basic dimensional analysis problem. The sort of thing that if you Google what is dimensional analysis, that'll come up. And it's really just an exercise in getting more comfortable with unit conversions. And then we'll talk about using unit conversions or using dimensional analysis as a trick to help you solve problems. And finally, we'll use it as a real trick for when you forget an equation or you have something you don't really understand how to do. So let's get started. Let's solve some problems with units first by solving a basic unit problem. If the speed of light is 3 times 10 to the 8 meters per second, what is the speed of light in furlongs per fortnight? Okay, let's get started converting meters per second to furlongs per fortnight. So we really want to think of this as 2 things. We need to convert the meters into furlongs and the seconds into fortnights. So we'll start out by writing meters in the numerator and seconds in the denominator. Let's start by converting the distance. So what I'm going to do is I'm going to say, well, I want meters on the bottom so it cancels out, and centimeters on the top. But how many centimeters are in a meter? Well, there's 100. I should have left myself more space. But I don't really want centimeters. I want to get over into my silly imperial units. So I have 1 centimeter, so I have 2.5 centimeters. You'll pretend that looks like 2.54 in 1 inch. And then I know I have 36 inches in 1 yard times 220 yards in 1 furlong, so 1 furlong on the numerator is 220 yards in the denominator. Now when I want to go through and get rid of all my things, I will cancel my meters with my meters, my centimeters with my centimeters, my inches with my inches, and my yards with my yards. Okay, so having worked out our units for distance, we now need to work out our units for time. So I have seconds in the denominator, and I want to convert that into minutes first. So I have 60 seconds in the numerator, makes 1 minute in the denominator, times 60 minutes in the numerator, makes 1 hour in the denominator. You do this long enough, and you'll pretty quickly discover that 60 minutes times 60 seconds is 3,600 seconds in an hour, but I've left it like this because that's less intuitive. And I know 1 day is 24 hours. Of course, astronomically, it's not exactly 24 hours, but that doesn't matter for this level of precision. And 1 fortnight, FTN, is 14 days. So to actually solve this problem, I will go through, I'll cancel my time units. The seconds cancel here, the minutes here, whoopsies, the hours here, and the days here. And then I multiply everything together. So in the numerator, I have my initial value, 3 times 10 to the 8, times 100, times 3,600, times 24, times 14. Divide all of that by 2.54, times 36, times 220. And so in the end, the speed of light in furlongs per fortnight is 1.8 times 10 to the 12th per font. It's a big cutoff, but you get the point. The second important way that we can solve problems with units is by doing a sanity check. helping us look at our answer and see if what we got was actually something that makes sense. Okay, so I have done a problem here and I have done it wrong. The problem says a sphere has a density of 0.01 kilograms per meters cubed and a mass of 1.5 kilograms. Calculate its radius. Now, the imaginary student here, which is me, wrote down correctly that the mass density was the mass divided by the volume, and therefore the volume was equal to the mass divided by the density. But here, this student has made a mistake. They've written that the volume is pi r squared, which isn't right. The volume is 4/3 pi r cubed for a sphere. And then they've solved the problem and they've come to an answer. Now this answer will be wrong because this equation was wrong. How could this student have used dimensional analysis to realize something was going wrong? That's a great question. Let's find out. Over here and write out what's happening in terms of units. So up here, rho is kilograms per meters cubed, which has to be equal to kilograms divided by, this volume has to be in meters cubed. Okay, good to know. So now let's come down here. So I know that my volume should be meters cubed, which is equal to kilograms divided by kilograms per meter cubed. Those kilograms will cancel. Okay, so far so good. Equals pi r squared. Well, pi doesn't have any units because it's just a constant. And this here has units of meters squared. Problem. These units over here don't match these units over here, which tells us that the volume is not pi r squared. Now, alternatively, I could have caught this slightly later in the problem by checking the units when I plugged in the numbers. Let me erase all this and get back to that. Okay, so when I went to plug in the numbers, I could also have said that I want r in meters equal to the square root of kilograms divided by kilograms per meter cubed times nothing, because pi is a constant. Okay, so I can cancel these kilograms, and so then I'm saying that meters should be equal to the square root of meters cubed. But that's not right. Meters are equal to the cube root of meters cubed. So I know that this isn't correct. I've made a mistake somewhere along the way, and therefore I already know that 6.91 is not the right radius here. For the sake of completeness, here's the correct solution to that problem. Now, sometimes in physics, we have what can only be described as a brain fart. We simply forget an equation or something important that we need to know. And so one of the things we can do to solve this problem is to use dimensional analysis. Suppose I have the following problem. A bulldozer is pushing a boulder with a force of 200 newtons. If the bulldozer pushes the boulder for 500 meters, how much work does the bulldozer do on the boulder? Suppose I get this problem and I say to myself, I forgot the definition of work. I don't remember. I have no idea. So what am I going to do? But I do remember something called the work-energy theorem, which says that the total amount of work done on a system has to be equal to the change in energy on that system when I add up all the different energies. This might seem a little weird. You remember the work-energy theorem, but you don't remember the definition of work? But anyone who's ever taken an exam can tell you that your brain does very strange things when you're in an exam. And in an exam context is generally when you try to use this trick. If you forget an equation when you're working on your homework, you should just look up the equation or ask the friend you're studying with. But on an exam, if you don't have an equation sheet, you're in a load of trouble. Well, what I know from the work-energy theorem is that the units of work and the units of energy have to be the same. And I might remember that the unit of energy is the joule. The joule. And furthermore, the joule is a Newton times a meter. Well, now I'm in business because I can make a pretty solid guess that at the very least, work will be proportional to the force times the distance. Now, I might be missing a constant, but at least I have a general sense that the force has to be multiplied by the distance. I might go ahead and say that the work has to be proportional to 200 newtons times 500 meters. Now, as it turns out, in the case where we're not having to worry about vector stuff, work actually is equal to force times displacement. But if I didn't remember that equation, and I just used my dimensional analysis to infer that it had to be something like 200 times 500, I would actually get the right answer, even if I didn't remember the equation. And had there been some other proportionality constant, maybe work was half of force times displacement, at least I'd get most of the way there, And I'd even make my physics professor very, very happy, because instead of just remembering the equation I was told in class, I would be thinking about what that equation meant and how I got there. Here's another variation of using units to solve your problem when you forget something. Imagine the problem says a force of 10 newtons can compress a spring 2 meters. What is the spring constant K for this spring? Now you either remember or you have written down on an equation sheet Hooke's law, which says that the force is equal to minus the spring constant times x. Now whether or not it has that minus sign, that's really dependent on your definition of various different quantities. So in this case, we'd say that 10 newtons equals minus k times minus 2 because we're compressing. That's just how we've defined the positive and negative directions. So coming back over here and solving for k equals minus the force divided by the displacement, which in this case is minus 10 divided by minus 2, which gives us a positive 5. Great, we're done. Except you know that if you write down just 5 and don't give a unit, your physics teacher will be really sad. But you don't remember what the unit for spring constant is, because how often in your life do you really think about spring constant? Not often. Fortunately, dimensional analysis is here to rescue you, because you know that that force was in newtons, and that minus 2, that compression, that was in meters. So you know that it has to be something like newtons per meter. Now, as it happens, that actually is the only unit we use for spring force. We just write newtons per meter. But in a universe where you had a more complex quantity here, and maybe the answer was not usually written as newtons per meter or some kind of combination unit, you can always write the combination unit, and often you'll just find yourself writing it in a further up the chain towards base units sort of way. And you're likely to get full credit for having written your unit, even if it's a slightly funky unit. So all this to say, units, they save your life. So this entire video is really just a plea from me and your physics teachers to you. Dimensional analysis. Please just do it. I promise it's not scary, and thinking a little bit about the units of a problem will help you avoid stupid mistakes and also help you remember things you might have forgotten in high-stress situations. It's also really good, and we didn't talk about this as much, but it also pairs really nicely with estimation and coming to problems you don't know anything about and trying to come up with what the answer might be. We'll talk more about estimation in the future, but in general, thinking about units is a great way to start thinking about physics problems a little bit more carefully and to make the whole process a bit less scary.